that you're here. But also this institute is a very interesting institute for those of you that don't know it. We do a lot of things, so you have a chance, maybe you can walk around also and talk to other people. We do cosmology, we do gravity, we do particle physics, we do string theory, we do experimental particle physics, we do plasma physics, we do nuclear physics, we do astrophysics, we have an astrophysicist group. We also do chemistry, radiation chemistry, and we also do, it's a very strange topic, but we do life outside of Earth. We search for life on Mars and beyond the solar system. So it's a very interdisciplinary institute that does a lot of very interesting things, but one of those things is actually cosmology. Thank you for Celia, that we're starting to do that here now in a more professional way. So I'm just going to finish here, and I want to wish you a very, very successful meeting. And also, again, welcome to the Institute of Nuclear Sciences. Thank you very much.
Well, so welcome all of you. My name is Celis Camilla. I am the organizer of this workshop for 2 days in this occasion. And I would like to say just a few words like a background about the history, about the invasion of this workshop. This workshop started as a meeting to have this kind of energy between different countries in the world, not only with Europe, but also this close relationship with all these countries in Mesoamerica. So in this occasion, as you see, we have our third edition. So we have also 2 editions before. These 2 editions were in Tuxtla Gutiérrez, in the states of Chiapas. And well, we started with a few people working in this workshop, but the main idea was to have this close relationship between these 2 areas like cosmology and gravity. And in some sense also to close the students and also the researchers with people not only in America but also in Europe. So I would like to show you just a few numbers about the results around this, the first meeting. So the first meeting was a really success. We have 3 people from other countries, and these 3 people offer main lectures around topics like, for example, black holes and something like cosmic background radiation. So in some sense, this meeting is, the purpose is to have 2 kinds of phases to abort in some sense, one from the gravity point of view and the other from the cosmology point of view. So the results for the first meeting was that we have a lot of relationship in the sense that we have the possibility to publish some papers. In this case, the 30% of the papers were released in this first meeting. Also, we have this collaboration with the students. Some of them are now working in Europe, for example. And another thing is related precisely with the development of thesis, not only bachelor thesis, but also for postgraduate thesis. And well, our second meeting was a bigger success in the sense that we are more people now, and in this case, well, we have the opportunity to have lectures also from Europe as well. In another point of view is that each year we always select 2 couple of subjects, principal subjects, like a hot topic of the year. So that last year the hot topics were the extended gravity studies and also something related with gravitational waves, like it's going to be this year, but more technical and with more professional point of view. And also, as you can see in this statistical information, well, the number of papers increases in comparison with the first edition, and also the development of thesis, in this case, postgraduate thesis. So now, in this third edition, we have the very pleasure to have a couple of researchers that came also from University of Glasgow, as Martin Hendrick is in here present. He's going to talk about gravitational waves. He forms part of the LIGO collaboration. And also we have Paolo Sallucci from Italy, and he's going to give you a very high quality point of view of what is happening with dark matter. So this is all the 2 couple of subjects, main subjects that we are going to discuss in this workshop, but also we have seminars and plenaries there is going to be like round ideas about these main subjects. So once again, I welcome all of you. I hope that you enjoy the next couple of days. Thank you.
Okay, good morning. Can you hear me? Yeah. Okay. Welcome to the third edition of the Mesoamerican Workshop of Cosmology and Gravity. I am Elias Castellanos. I am also an organizer. I'm coming from the MCTP of the University of Chiapas, and I'm going to be very brief because Elia says almost everything about the workshop. So I would like to thank the Mesoamerican Centre of Theoretical Physics of UNASH, also to the Institute of Nuclear Science for financial support, and all the colleagues for helping us in the organization of this workshop. And all of you, of course, our lecturers, thank you very much for coming. And I think that's all. Good morning, thank you very much. Welcome to Mexico. Welcome to the third edition of the workshop. Thank you very much.
Thank you, so let's get started.
Okay, sure, yeah. Just one other question. Is it possible to switch off? Yeah, oh, perfect. It's done, already done. Yeah, wonderful. Okay. Listo.
Yes, so well, I have the pleasure to present you the Professor Martin Hendrick. He's a very good friend and collaborator. He comes from the University of Glasgow. He's official senior member of the LIGO collaboration. And also, also we are members of the Royal Astronomical Society. So he's going to talk about gravitational wave astronomy and opening new window on the universe. So let's welcome him again, please.
So I think I have the microphone, okay. Buenos dias. Already, of course, people have been greeting you in English. So just to be a little different, I wanted to begin with just a very few remarks in Spanish. Estoy muy contento de volver a México. Es mi primera vez hasta más que 20 años y el mundo es muy diferente hoy con los detectores LIGO y las ondas gravitacionales. Estoy al mismo tiempo contento de mirar la bandera de Escocia por aquí porque parece que en este momento en mi país, el Reino Unido, el gobierno es muy loco porque Brexit es muy complicado y prefiero entender la relatividad general de entender Brexit. So, es porque estoy muy contento de estar por aquí. Ok, mi español no es mal. No es mal por la vida, para comer, para beber, pero por la ciencia es un nivel demasiado difícil. Por eso voy a cambiar a inglés, pero ensayo de hablar sencillo y muy claro. So, good morning everyone. As Celia has said, I am a member of the LIGO scientific collaboration. When I visited Mexico more than 20 years ago, I was working in cosmology. I spent time in Puebla and visited a few times to UNAM. Already even then, some colleagues in Glasgow were working in gravitational waves. They were trying to do the impossible, as some people said. They were trying to persuade our authorities to build a gravitational wave detector. Most people thought they were crazy, but because I had coffee with them a lot and had many discussions with them, even in the 1990s when I was coming here to Mexico to work on other topics, I was very interested in the possibility to detect gravitational waves. So all of these years later, what has happened is that I joined this collaboration about 15 years ago, and during the last few years, we have seen this remarkable goal become reality. So my colleagues in Glasgow and other colleagues around the world had been working hard for more or less 40 years to try to make this dream a reality. And I want to share with you in these lectures some of what we have achieved. Mainly I will talk about that tomorrow. Today I'm mainly going to concentrate on how we detect gravitational waves and how we extract information from the data. So first, just another few words about who I am. So I am Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow. So in the past, I was mainly working in cosmology. Right now, it's mainly gravitational wave astrophysics. Really, my dream is to use gravitational wave observations to do cosmology. And we are just beginning to do that now. So I will describe a little of that tomorrow, and also to look ahead to the future, to what we might do with future projects and future missions. So the kinds of questions that we dream to answer are to understand the nature of black holes and neutron stars, to understand what happens when they collide. We are already beginning to answer some of those questions, but there are many more questions to answer. As always seems to happen in science, you answer some questions and new questions emerge that you did not even expect before. I am also someone who is very passionate about general aspects of Einstein's theories. This was taken some years ago visiting to Washington, to the statue of Einstein, and in fact, when I was appointed to a faculty position, the day after the interview, I had to begin teaching a course in General Relativity. So this was a tough challenge for my first semester. In fact, when I did come to Mexico before, it was a younger version of me. I was also very passionate to visit many parts of your country and to learn about the rich history of archaeoastronomy here in Mexico, which we also share in some parts of Scotland and the rest of the UK. As I said, however, the world has changed a lot since then, and now my world is dominated by the LIGO scientific collaboration. It means that every day there is a telecon with someone somewhere in the world. And we're a big collaboration, and of course I am not here to speak for everyone. We all have our specialities, our areas of expertise. So mainly I will concentrate on data analysis, but I will try to describe just a little about how the detectors actually work. I didn't build them, I'm not an expert in that, but I've learned a lot from talking to my colleagues in Glasgow who pioneered this work for many decades. So, we announced the first discovery of gravitational waves in 2016, more than 3 years ago, but in fact the detection occurred in September 2015, more than 4 years ago. It took us many months to be absolutely sure that we had made the detection. There are several reasons for this, and I want to use this lecture today to explain some of those issues and complications, specifically to understand the noise properties of our detector, which made the biggest challenge with that first detection. You do not want to announce you have discovered gravitational waves and then later announce that, sorry guys, we got it wrong. So it took us many months. But we have got better at the data analysis since then, more efficient, faster, and we are now in a position where we are sharing a lot of resources with other people so that anyone can learn about the data analysis methods and analyze some data for themselves. So I want to also use today's lecture to explain a little how you can do that for yourselves. You can access some of our published data. We've discovered a lot of sources, not just that first one that was announced in February 2016. In December of 2018, we published a catalogue of binary systems merging black holes and one merging neutron star system. These were detected during the first 2 observing runs of LIGO and also Virgo, our sister collaboration. The Virgo detector is in Italy. So these runs took place between 2015 and 2017. And then the detectors were upgraded to make them more sensitive. And we began, after publishing this paper in December on the archive, in fact it was in September, just a few weeks ago, that it was published in the journal, PhysRevX. But in between that, we actually began observing again. Our 3rd observing run began on April 1st, 2019, and since then we have seen 33 more candidate gravitational wave events. We cannot be sure that all of them are real. The reasons for this are connected to the difficulties we have with analyzing the data, so I will discuss some of that later this morning. Tomorrow I will focus on some of the things we have learned from the events we have published as confirmed gravitational wave signals, and also what we are learning from these candidates. And I also want to share with you the process with which we alert everyone when these candidates are detected, because we now share that information more or less immediately, so that astronomers around the world can use their telescopes to look for an electromagnetic counterpart. So that has been a very big change since the beginning of gravitational wave astronomy. And of course, you can take part in those searches. Astronomers here in Mexico, astronomers in any country where there are clear skies and there are telescopes are encouraged to become involved. Another responsibility I have for the LIGO collaboration is to chair the Education and Public Outreach Group. So for 10 years now, we have been trying to communicate the science and also just the excitement of gravitational wave astronomy to everyone, not just to other scientists. And that's been a lot of hard work, but a lot of fun presenting our discoveries at science festivals, at museums, in high schools, to anyone who is interested. And believe me, lots more people are interested now because we have actually detected something. In fact, you can maybe see, even Albert Einstein was quite interested. He came to one of our science festivals and he took my autograph. So that was very nice. So, in case I forget at the end, because most of my presentation this morning is going to be quite technical, focusing on the science, but let me also emphasize that there are many good resources aimed at a more general audience. So maybe some of these will be interesting for you, but also if you are involved in doing outreach yourself or teaching undergraduate students or maybe teaching high school students, some of these resources could be useful. So you can find lots just on our website, ligo.org. So as I said, the main focus of this first presentation this morning is to try to understand the methods that we use to detect gravitational waves and how we can analyze the data to learn about the signals. So I propose to talk until about maybe 10 o'clock, and then we will take a short break and come back again for the remainder of this first session. So let's begin with this question, what are gravitational waves? But let me emphasize again, please, if you have any questions as we go along, just ask. Or, of course, come and talk to me at the breaks, but please don't feel that you need to wait. You can ask questions anytime. So, gravitational waves we understand in the context of Einstein's general theory of relativity. As I said, much simpler to understand than Brexit. But okay, I don't want to assume that everyone has studied general relativity before. So let's begin with some gentle reminders or some gentle introduction about the key physics ideas of general relativity. So often we use an analogy. It's not perfect. it misses some important mathematical details, but I do find it very useful to give us some visual picture of what gravity is in Einstein's framework. So probably you're all familiar with this at some level, the idea of space-time as a stretched sheet of rubber. And that means when you drop something into such a sheet, it will bend. So gravity is a manifestation of space-time curvature, and a nice phrase that was suggested by John Wheeler tries to capture this. He said that space-time tells matter how to move, and matter tells space-time how to curve. So general relativity, as I'm sure everyone knows, was published in the early 20th century, 1915, 1916. So we were celebrating the 100th anniversary of that theory when gravitational waves were detected. So gravitational waves are a prediction of general relativity in the sense that if that space-time curvature is changing, then it produces waves which spread out through the universe according to general relativity at the speed of light, and that is what we are trying to measure. Okay, so much for the simple picture, but if we are trying to understand this in terms of quantitative physics, then it starts to get a little more complicated. So we've got Einstein's field equations, we've got on the left-hand side the so-called Einstein Tensor, which describes the curvature of space-time. So tensors, think of them as generalizations of the geometrical objects we meet in undergraduate studies generally, vectors and scalars for that matter. Tensors are more general because they need to be to describe the geometrical structure that we encounter in curved space-time. And Einstein formulated his theory within that mathematical framework because it has a lot of nice properties. But I don't want to get too bogged down in those properties today, in case people have not encountered this before. If people are interested to explore in depth the full mathematical treatment, of course there are many textbooks out there, but there is also a set of lecture notes which I wrote some years ago, about 100 pages, which effectively is like a small textbook, and maybe a little shorter than some of the other textbooks which are out there. So I will give a link to these notes, and you're very welcome to download those for afterwards. But just in a few minutes, I want to try to capture some of the essential ideas that are important in the context of gravitational waves. So I mentioned this tensor on the left, and on the right-hand side, we have another one, teeny new, which expresses the energy and matter content of the universe. So basically the phrase we had before, space-time tells matter how to move, and matter tells space-time how to curve, well, really we should say matter and energy tell space-time how to curve. This is the mathematical version of that phrase. And it was described by Max Born as a great feat of human thinking. And, well, I think it is. But to understand the mathematics in detail requires some of those 100 pages that I mentioned. So we will be very brief this morning. Really the main thing that I want to focus on is the constant of proportionality, because that's crucial in understanding why it took us 100 years to detect gravitational waves. That constant of proportionality we can calculate, we can estimate by making an assumption about boundary conditions. And the assumption is that if we are in a weak gravitational field, then we expect these equations that look a little weird, they are tensors, but we expect them to simplify to the version you would have in Newtonian gravity. And if you go through that analysis, which is in my longer notes, to go through it, it's also in many textbooks, so maybe some of you have seen that before, but in the end you show that the constant is 8 pi g divided by c to the power 4. That is a very small number, and that is crucial because it means that you need a very large amount of mass and energy accelerating in order to produce a change in space-time curvature that you could measure. I mean, this is an accelerating mass. Technically, it's producing gravitational waves, but they are so incredibly tiny, you could never hope to measure them. In tomorrow's presentation, I'll repeat that point. Maybe we will have a slightly different audience, but I just want to emphasize that the number is really small, and we will actually calculate it tomorrow. But all of that means that we need the universe to be our laboratory. We need to be provided with very powerful sources of accelerating mass and energy to measure the changes in space-time curvature. That's why it took us 100 years to develop enough sensitivity to be able to detect those tiny changes. So just a little bit more mathematics to help us make sense of this. The equations of general relativity, the Einstein equations we saw before, we can ultimately construct them starting off with a very fundamental function that we call the metric, which characterizes the geometrical properties of our space-time. And we are thinking about a situation where that metric is nearly flat. In fact, if you are considering the generation of gravitational waves, then you need to consider a more extreme situation where the metric perturbations can be really large. But I mainly just want to think about detecting gravitational waves, and by the time they reach us, they are very weak. So our space-time metric is almost like the flat metric of special relativity. So that's the eta alpha beta. So we are talking about a perturbation, h alpha beta, which is going to be small. The alpha and the beta, they are labels to denote our coordinates. So for example, this could be time, x, y, and z. And the alpha, beta are, and therefore, altogether representing many different components. And because there can, in principle, be many different components, it's always a good idea to choose our coordinate system wisely to simplify these equations. So there's a lot of detail involved in that, again described more completely in my longer notes, but all we need to know is that we can choose a coordinate system in which these equations take a very simple form. And in fact, they take the form of a wave. So a particular choice of coordinate system called the transverse traceless gauge is the one that we're going to consider. But more generally, we can have wave-like solutions. This is really the key result that the idea of gravitational waves comes from, is to think that metric perturbations propagate as waves in free space at the speed of light. I mentioned this transverse traceless gauge. That just simplifies things a little bit more, a particular choice of gauge, and in that way of setting up the equations, then we basically find that these wave amplitude coefficients can be greatly simplified. So in fact, we firstly can show that there is no component of the metric perturbation, the gravitational wave, in the direction of propagation of the wave. So if the wave is propagating this way, the disturbance is transverse to that. That's why we call it the transverse traceless gauge. Well, what about the traceless part? Again, that's just something you can work through some algebra to show. So what we have is zeros everywhere apart from these four terms, and this one plus this one equals 0. So it's traceless. So this is about as simple as we can get. There are basically just two amplitude components that are non-trivial because of the symmetric nature of the metric as well. We just need to think about this one, AXX, and then the AYY will be minus that in this particular choice of coordinate system. And then there is also AXY, which also appears up here. So these two terms, if we consider them separately and set one of them equal to 0 while the other one is not equal to 0, that gives us two like orthogonal solutions that we can consider. We think of these as polarizations, as disturbances of space-time that are sort of fundamentally describing the properties of the wave. So if we take the one where, it's probably rather small to see, if we take the one where AXX is not equal to 0, we call that the plus polarization, and the way that space-time distorts is that it squeezes in one direction while it stretches in the other. And, well, we can show it as a series of still images at different times, different phases of the wave, or this is a little animation. I'm not trying to hypnotize you, but that's what it appears like. And then the other one is just rotated at 45 degrees to the plus polarization. We call it the cross polarization. So those are our building blocks for our gravitational wave, these two polarization states. So remember, the effect of the wave is to squeeze in one direction while stretching in the other. So this provides us with a fundamental insight into how the detectors themselves work. They are laser interferometers. The purpose of having the laser interferometer is to try to detect changes in the properties of the laser light going this way compared with the laser light going this way. So all of the ground-based detectors are L-shaped, the arms at 90 degrees apart. There is the LIGO detectors here. This is Virgo in Italy, and this one is GEO, which is in Germany. So again, just to think through some of these basic ideas a little more. Let's say we have a plus polarized wave propagating along the z-axis, that means out of the board towards you. The effect of this quadrupolar distortion, as we call it, because it's squeezing in one direction while stretching in the other, it's a quadrupolar pattern. That effect will be to change the proper length of one of those arms. So in those interferometers, the basic setup is to have a laser light that is split, and one beam goes one way, one goes the other, and bounces off a mirror. So the proper distance traveled by the laser beams will be affected by the passage of the gravitational wave. So there's a change of delta L squeezing, and then delta L stretching at different phases. And we relate that to what's called a strain, a dimensionless strain, denoted by H, which is actually that same number, the scalar version of it, that we saw before, the H alpha beta, the metric perturbation. So this is directly linking the effect on the arms back to the metric perturbation. The problem is that these signals are so weak. Like ripples in a pond, by the time they reach us, they are incredibly weak, and the kinds of changes in arm length that we are trying to search for correspond to movements of less than 1,000th the size of a proton. Or to give, well, I'm in an institute for nuclear physics, so of course this is a safe place to talk about 1,000th of the diameter of a proton, but another useful comparison for a public audience is to take one of your hairs. We are talking 1 millionth the width of that hair. So it's no wonder it took 100 years to have the technology capable of detecting that. How does it work? Well, we already saw the photos of LIGO. The two LIGO interferometers are in Louisiana and Hanford, Washington State, 3,000 kilometers apart. So that idea of splitting the laser light, again, this is a simplified cartoon, but I think it's quite useful. What we will see is that as a gravitational wave passes by, hugely exaggerated, but we can see the change in the phase of the laser light so that the interference pattern is changed. This is why LIGO is a laser interferometer. We are using the interference pattern as a probe of the strain, the quantity h, and how it changes in time. But there are many sources of noise. This is the part I am not an expert in, but I've tried to learn from my expert colleagues, and really the main points to stress are that the noise is dependent on frequency. So we are trying to measure the dimensionless strain h We are trying to measure very small quantities, 1 millionth the width of a human hair, even with an arm length of 4 kilometers. So that means the strain is about 10 to the minus 21 or so. And the sources of noise come from many different directions. There is quantum noise to do with the laser. That's most serious at high frequencies. But there are also seismic noises because the ground shakes, which are especially important at low frequencies. And in the middle, there are noises to do with the thermal excitation of the mirrors. And the mirrors are not just sitting there, they are suspended so that we can try to isolate them from the surrounding environment. But at those middle frequencies of a few tens of hertz, well, even the suspension of the mirrors introduces extra thermal noise. So the object is to make these noise sources as low as possible so that you are sensitive to smaller strains. And we can do that quite well in these middle frequencies from about 10 hertz to maybe 1,000, but then the noise rises very sharply outside of that range. So we are limited in the range of frequencies we can access with the ground-based detectors. And those detectors operated for some years. They operated in the LIGO sites, also Virgo, GEO that I mentioned, and indeed some facilities in Japan. Japan is just about to begin operation with a new detector. I'll say more about that tomorrow. Of course, during this period, 2002 to 2010, we didn't detect anything. If we had, you would have heard. But then in 2010, we began to upgrade the LIGO detectors, to turn them into advanced LIGO, to make them more sensitive. So how did we do that? Well, at high frequencies, we used more powerful lasers. So this was gaining us something like 1 order of magnitude improvement in sensitivity. That was mainly led by our colleagues in Germany at the Albert Einstein Institute and Max Planck Institute, but with a lot of other groups around the world contributing. And then at low frequencies, that work was mainly led by the UK, mainly led by our group in Glasgow. And the chief difference was to improve the seismic isolation of the mirrors on the end of the arms, to replace the steel wire, like piano wire almost, that was suspending the mirrors before, to replace that with silica fibers, and to join the silica fiber with the mirrors, which were also made heavier, in a very sophisticated way, always trying to minimize the thermal noise. So this gain at low frequency was really important for the very first detection, because I'll say more about this tomorrow, but if you think about it, we detected nothing for a decade. We began operations in September 2015 with this upgraded new advanced LIGO suspension system. And we were expecting to begin taking data on September 18th, but we were ready 1 week before. So we began taking data early, and we detected something within just a few days. Some people were surprised by that. They thought something must be wrong. We saw nothing for years, and then suddenly we see something almost immediately. But there's a very good scientific reason for that, because we had improved the low frequency sensitivity, and the first signal that we detected, as we will see in the coming minutes, was quite massive black holes. Their merger frequency was lower than we had really been searching for with initial LIGO, because they were more massive than perhaps we expected black holes ought to be. So the type of source that we were sensitive to really required improving that low frequency sensitivity. This was very good news for my institute because we had contributed that part to the overall story. So here is that signal that we saw. And of course, you've maybe seen this before. It's been on t-shirts and posters all of the time since 2015 or 2016. So what we believe we detected was the in-spiral and merger of two massive stellar black holes. So what I want to do now is to help, I hope, to convince you why we believe that. And to do it using some basic physics, not too much general relativity, but just to use the data themselves and try to understand the physical arguments why we believe this must have been two black holes. So this is the detection paper. It's got more than, I think, 4,000 citations now. You know, I wrote some sentences in it, so I can claim some credit, but of course it was a huge team effort to get this done. One of my other jobs for the collaboration that I mentioned is to chair the education and public outreach group, and one of the things we do is we produce for every paper a science summary. These are designed for maybe high school students or physics teachers. We remove a lot of the technical details, but we still try to be true to the physics results and to the scientific conclusions. So you can download these summaries for any of our papers, but I wrote the one for that first detection paper. I'm very proud of it. A lot of people have said it's the best thing I've ever written. Now, I wrote this version. I didn't write this one. This is the Spanish translation, but you can download that too. It was my friend and colleague Alicia Cintes and her group in the Islas Baleares that they translated. And this was in the last days before we announced to the public our discovery. So one of the things we wanted to do with the science summary was to answer this very specific question. How do we know GW 150914 was a black hole merger? So that's what I want to discuss with you for these next 20 minutes before we stop for a break. So the summary is quite short, only 4 pages, and to answer this question, we just really devoted 2 short paragraphs. And there are no equations and not many words. But actually, you deserve a more complete explanation. Essentially, the argument is this. By analyzing the waveform, we could estimate the masses and the separation of the bodies that were merging. And those masses and separations really argue that it must have been black holes. Put it this way, if they weren't black holes, they must have been something even stranger, because they were so massive and so close together. So let's see if we can understand the argument based on the physics you all know. In fact, we wrote another paper which is more similar to what I am going to discuss. This was written in August 2016. It's in the Annals of Physics, but actually it's probably behind a paywall, like so many journals these days, so you can find it just on the archive. That's the reference. The paper is called The Basic Physics of the Binary Black Hole Merger, GW 150914. Our objective was to demonstrate that we can understand the physical properties of this event without requiring very much general relativity. So the game plan of the paper is to use the data itself to estimate the gravitational wave frequency and how it changes. Just use the data to do that. Then use a little GR theory to relate the gravitational wave luminosity and the source masses. In other words, to estimate what the source masses were. And then use some simple orbital dynamics to work out the separation of those masses. Okay? So that's what we are going to do now. So the basic setup we have is 2 masses orbiting around each other. And I just remind you that if you have a mass m, then the Schwarzschild radius corresponding to that mass m is given by this formula. So about 3 kilometers for 1 solar mass. and it scales linearly. So here's the data from that first detection, and even just for high school physics, we could look at that graph and we could roughly, very roughly, estimate the frequency from the data just by looking at the separation in time of the peaks. This would be very approximate, but that's the spirit in which I want to think about this. If you want to do the analysis more rigorously, then we'll discuss that after the short break, when we look at the data analysis methods. But first, I just want to see if we can roughly get a feel for the numbers. Maybe it's a little better to use a time frequency plot. I will show you after the break how we produce these. But here's the one for the first event. You can see what's called a chirp. It's an upwardly sweeping signal. So the frequency increases with time very rapidly towards the end, and the amplitude increases also. If you produced it as a sound wave, maybe you've heard these files before, it would sound a bit like this. Actually, it would be lower pitch than that because it's very massive, as we will see. We will discover that the masses of these black holes are quite high. So, what is the maximum frequency that we would associate with this event? So again, we can just make a very rough estimate. I would say that even just by eye, this frequency looks to be peaking at least at 150 hertz. Okay, so the first slightly non-trivial bit of physics that we need is to realize that the gravitational wave frequency is twice the orbital frequency. So one way to see that, maybe in a simple way, is that the gravitational wave signal is produced by accelerating masses, and as these masses orbit around each other, they will return to the same configuration after only 1/2 of an orbit. Well, it's not really the same, because M1 is over here, M2 is over here. When M1 goes around to here, of course it's on the other side, but there's a symmetry there which indicates, also as you can see from the quadrupolar pattern, that 2 times every orbit the two masses are on the same line with respect to our coordinate system. So basically, that means that the gravitational wave frequency we expect to be twice the orbital frequency. So if we are estimating the gravitational wave frequency to be 150 hertz, that means we are saying that the orbital frequency is 75 hertz. That means these objects are orbiting around each other 75 times every second. This is quite dramatic compared with many astronomical events. Okay, we need a little bit of GR to go any further, but I'm trying to minimize that so we can focus on the basic physics. So in Einstein's 1918 paper, he predicted what the gravitational wave strain, the metric perturbation, just like we saw in the early slides, he predicted what that would be as a function of the disturbance in the mass distribution. So we characterize that in terms of a mass quadrupole moment, and it's its second time derivative, but here's that constant of proportionality again. So we've got g over c to the fourth, just like we talked about before. And then the metric perturbation is inversely proportional to the luminosity distance. So that's a distance measure that we use a lot in astronomy and cosmology. We are accustomed with light to the flux being inversely proportional to the square of the luminosity distance. But that's because the flux is related to the amplitude of the electric and magnetic field squared. Whereas because we are measuring directly the amplitude of the gravitational wave field, the gravitational field, and how it's being perturbed, then this is proportional to 1 over d instead of 1 over d squared. There's some more rather unattractive mathematics, which basically gives us an expression for how the energy emitted in gravitational waves depends on time. And notice that that now involves the third time derivative of the quadrupole moment. And in fact, it involves the product of that term with itself and then summed over the different coordinates. And there's an integral over a sphere at radius dl, because the gravitational waves are emitted in all directions. So that quantity on the left-hand side is crucial. It's the rate of loss of orbital energy to gravitational waves. There's a bit more notation over there on the right. The details don't really matter. You can look at the basic physics paper from the archive if you want to read the rest. After lots of algebra, which it would be really boring to go through, the algebra simplifies to this, that the rate of change of the gravitational wave energy emitted is 32 over 5 times g over c to the 5th power now. And then there's a couple more things I should just define. There's a reduced mass, mu, which is the product of the masses divided by their sum. And then there's r, which is the separation of the two masses. That's r to the 4th power. And then we get an omega to the power 6. That's the orbital angular frequency, which is half the gravitational wave angular frequency. So the 6th power is coming from the fact that we've got essentially 6 orders of differentiation taking place. Okay, so even before our detection of gravitational waves in 2015, we had a good sense that all of this agreed with reality, because maybe you know there was the binary pulsar system observed over many years from the Arecibo radio telescope in Puerto Rico. And Russell House and Joe Taylor, they were awarded the Nobel Prize for Physics for their study of this system. And that study included realizing that the orbit is shrinking. I think I had the number on the previous slide. It's shrinking about 3.1 millimeters per orbit. And in fact, that shrinking we interpret as because the system is losing energy through the radiation of gravitational waves. But those two neutron stars are still very far apart, so the radiation is emitted at very low frequencies of gravitational wave emission, too low for LIGO to detect. But one of the motivations for building LIGO was to look for systems like this, where the masses were much closer together and radiating at much higher frequency. But this system gave us confidence that that was not a crazy idea, because indeed it appeared that this system was doing just that. So we've got an expression for the luminosity in gravitational waves, that's the dE by dt, and if we relate that to the change in the orbital energy, we actually can just get a good answer using a simple Newtonian expression. So we have the orbital energy minus g mu over 2r. We differentiate that, we get a term involving r dot, and we're going to relate that to minus the gravitational wave luminosity. And then we can use Kepler's third law to relate the radius and its derivative to orbital frequency and its derivative. So from Kepler's third law, we have that r cubed is gm over omega squared, and that implies that r dot is minus 2/3 times r times omega dot over omega. So that gives us a number of equations to combine. So those are the three equations we had on the previous slide, and there is the one from 2 slides back, which is d by dt of the gravitational wave energy. Again, there's a lot of rather boring algebra, but it's there if you want to do it. Eventually, what we get is an expression for omega dot cubed. So what it says is how the frequency derivative depends on the frequency. So it tells us that at any given instant, the system will have a frequency, but that frequency will evolve. It will increase. And the other term that's come in is what we call the chirp mass. It's a combination of M1 and M2 with these particular powers. We are almost done with what we want to try to do. We want to rearrange so that we get an expression for the chirp mass, because we would like to estimate that from the data. So the chirp mass, just rearranging that formula before, and now introducing the gravitational wave frequency, which is twice the orbital frequency, and we drop the factors of 2 pi and we absorb all that into the rest of the expression, we get this. We get c cubed over g, and then we get something involving the frequency and the frequency derivative. So if we can measure the gravitational wave frequency and its derivative, we can estimate the chirp mass. So this derivation is crude. Of course, we do it much better. We use numerical relativity to predict the waveforms more precisely. I'll talk about that later. But this is just to give us the general idea. And of course, it's easy to say that this is what we do, but to actually do it from these data would not be very sensible. I mean, to measure the frequency is just about possible. To crudely estimate it from the separation of the peaks, but the frequency derivative, that would be maybe taking it too far. But alternatively, what we can do is take this equation and write it as a separable differential equation for time t. And then if we impose a simplified boundary condition, which is that the gravitational wave frequency tends to infinity as t tends to the merger. I mean, that doesn't actually happen. The numerical relativity calculations show that the frequency peaks, but it doesn't go to infinity. But we're just looking for the general trend before you get to the merger, because we know that this simple treatment would break down then anyway. So that gives us an equation we can solve. A differential equation for the frequency as a function of time, well, this power of the frequency, expressed in terms of the chirp mass and time. And then that means we can just read the frequencies from the time frequency plot. Again, it's very simple, simplistic, but it's easy to do. What does that give us? It gives us this graph. So what you see here is the frequency to the -8/3 power as a function of time. So basically up here is where we expect the merger to be, and then this is earlier times. So we're using this equation. The green dots are obtained from that time frequency plot. The best fit curve, the best fit line, is the green line, and that corresponds to a chirp mass of 37 solar masses. But of course the analysis is very crude, very simplistic. So maybe a more conservative thing to do is just to say, well, it's of course not really a straight line, but let's just try to get some bound on the value of the chirp mass. So the blue curve is a chirp mass of 30, the red is a chirp mass of 40. So all I would want you to believe from this is that we seem to have good evidence that the chirp mass is at least 30 solar masses. So let's say that's our conservative estimate, and let's say for simplicity that we take M1 to equal M2. It doesn't have to. Our basic physics paper talks about what the effect of an unequal mass ratio would be, but for now let's just take them to be the same, and that gives us M1 equals M2 equals 35 solar masses. And then crucially, if the 35 solar masses, and we use Kepler's third law applied at that maximum frequency, we get a separation of 350 kilometers. So what we've basically got is two objects of about 30 solar masses, or slightly more, separated by only about 2 times their Schwarzschild radius. As far as I'm concerned, they have to be black holes, unless there's something else that we might consider even stranger that we haven't met before.
Question?
Sure.
Out of the context of gravitational wave, which other astronomical system have been observed such huge black holes?
Well, there are plenty of astronomical systems where indirectly we have evidence of even more massive black holes, supermassive black holes in the center of galaxies. But what's different about this is we have 2 which are close enough together that they are radiating gravitational waves. We also have evidence of stellar mass black holes indirectly inferred from, let's say, X-ray observations, because you probably know this, everyone will know, you can have black holes orbiting a more regular star and accreting matter from its companion. So the rate at which it accretes tells you the luminosity in X-rays, and that also can be related to the mass of the black hole. So the idea that you have a stellar object with a mass of 30 solar masses is not that unusual. You can have ordinary stars on the main sequence which are that massive, but they are much bigger than 350 kilometers. And to have 2 of them so close together, the only candidate I can think of is a black hole. So I think for that reason we were justified in calling our detection paper Observation of Gravitational Waves from a Binary Black Hole Merger. And in fact we just used the same title for our science summary, the simplified communication of the same ideas. And that's also why when the announcement was made in February 2016, maybe some of you saw this on the web or on TV, there were several very famous people present. They would later win the Nobel Prize for this discovery. One of them was Kip Thorne, who has been associated for many years with black holes. And at the beginning of the press conference, there was a short movie trying to imagine what these objects would look like close up. And there were many interesting aspects to this because, and the movie won't play, it's a very big file, but you can find it on our LIGO.org website. It shows the distortion of the light from the background stars. This is just an artist's impression. No one knows what the star pattern would be because the source we could also deduce was about 1.3 billion light years away. But we think that the light from these background stars would have been distorted by gravitational lensing just before they merged. So I think I want to stop there. Let me just say what's coming up after we have a short pause. This science summary, we've talked about the argument why we think they are black holes. But the other argument I want to focus on in the second half of this first lecture is, are we sure that it was a real astrophysical event? And what I will do in that part is describe and discuss our data analysis methods. Mainly again focusing on this first detection, but also beginning to talk about some of the other detections also. Okay, so I think let's stop for 10 minutes. Thank you very much. So yeah, this is not too fast, is it? It's okay?
No,
Good.
it's okay.
Very quick.
It's really quick.
Hello. Sure. Let me switch off the microphone so we don't broadcast to everyone. think so.